this year, joint talk between CSES and ARU. It gives me great pleasure this evening to welcome Dr. Stephen Cutts, who's going to do our talk today on spacecraft propulsion. But I was just saying, he's got a very interesting career. Stephen studied physics at Imperial College and medicine at St Thomas Hospital in London. He has a lifetime interest in the exploration of outer space, and his sci-fi novel, The Village on Mars, was published 5 years ago. He's previously written for the Independent, Spaceflight magazine, Astrologia magazine, The Guardian, The Daily Telegraph, and The Sunday Times. So I think that's a pretty nice sweep. I'm sure we're going to have a really interesting talk, and it's really good also to see what a large number of people we've got here tonight. And I see new faces too from our regular series, so that is very encouraging. But without further ado, Stephen, I'll hand over to you. Stephen will take questions at the end of the talk. Thank you.
Okay, so this talk is about spacecraft propulsion. I'm slightly apprehensive there's too many slides. We won't get to the end, so I may have to cut a few out. Someone wave to me if we're going on for too long. I may start talking too quickly, so warn me about that too. So the first talk I gave, when I first started doing it, was to try to promote that book about Mars, because the company that was going to run it went bankrupt. So I decided to try to promote it myself through science talks around the country. We sold a few copies out of the cardboard box. But a lot of people commented in the Mars talk. I mentioned in passing that there's been very little advance in propulsion of rockets since the early 1960s, which is in some respects still true. But since I first gave this talk more than 10 years ago, there actually has been some progress. So we'll talk about rocket propulsion. And this talk focuses primarily on the difficulty in getting from the surface of this planet to low Earth orbit, which is the fundamental problem in space travel. So here's a picture of this chap who's actually a physicist himself. This is Robert Goddard in America. He's credited with being the guy who flew the first liquid-propelled rocket. Solid rocket motors have been around for centuries, and fireworks and things. If you use gunpowder, there's a fundamental limit how fast the rocket can go because of the chemical combination, the energy stored in the propellant. There's also the problem with solid rocket motors, you can't turn them on and off. Once you turn them on, they burn out. With liquid propellant, in principle, you can turn it on and off and throttle it and so on as you want to. So he's got the credit for that. Now, how do you live to a grand old age? Would he live long enough to see the Apollo 11 fly to the moon? But he died relatively young. And he was actually ignored in America, unfortunately, by a lot of people. With the Germans really taking over rocket propulsion lead during World War II. Here's the V2, which is a German missile developed to hit Britain. And at one stage, the British were discussing whether or not to blow up the research facility where it was being developed. And part of the reason it was the authority to do it was they were advised by British engineers it was impossible for the Germans to have developed a missile of this capability in the time schedule of the war. It was fundamentally impossible. It could not be a rocket-propelled bomb. In fact, it was. Okay, the V2 in particular was impossible to intercept and then quite damaging. Anyway, after the war, the Russians and the Americans captured a lot of these twos. The British had a few too, and they learned how the Germans had done it. In fact, they used a lot of the German scientists on the project to develop both programs. But the American program being more influenced by Germans than the Russians, but the Russians had some Germans that they captured too. So supposing on the surface of the Earth, represented by this magnificent diagram here, the Earth, and we take off with a rocket, we go to a certain altitude, we fall back down again, okay? But if we have a more powerful rocket, we get to a higher altitude, and we fall back down again. But if you get progressively faster and faster and faster, eventually what actually happens is you fall, you actually miss the Earth because it's a ball, it's round, you can keep going. And what in effect happens is the centrifugal force of the rotation equals the gravitational force of the center of the Earth. And the speed required to do this is 5 miles a second, 17,000 miles an hour. Okay, so that's the minimum speed that you have to have. Less than that, you'll fall back to Earth. So he would be coming up to an altitude, we need to be above the Earth's atmosphere or we'll just be pulled down by drag, say 200 miles or above, and we'd be going down range at 17,000 miles an hour, okay? But it's quite important to ascend vertically quickly, because you don't want to hesitate halfway up and burn off fuel with no gain. You want to get above the thicker part of the atmosphere and the lower part of the atmosphere as fast as you can, and then drop sideways into your orbit. So the atmosphere, in fact, is hugely dense low down. In fact, even if you go in an elevator in a tall building, your ears can pop because of a change in pressure. But when it becomes tenuous, it gets progressively more tenuous, really to quite a great height. You've got to be really above the ionosphere to stay in orbit, otherwise the drag will pull you down. In fact, a few molecules will be loitering at the altitude of the International Space Station, say 250 miles, which over a period of several years will slow you down. Eventually you enter the atmosphere, and every so often they have to have a rocket-propelled vehicle that pushes the space station higher. Otherwise we'll burn up at a very high altitude, to the moon for example. That doesn't happen because we're way above the atmosphere. So if you think about experimental rockets we might want to build, here's at the top, a relatively small one, and this would have a burnout speed of 1 mile a second, okay? This one here would be 3 miles a second, and this one would be 5 miles a second. So our prototype, I guess we could do 1 mile a second and progress to 5. But for orbit, we've got to go to 5, which is 5 times faster than 1 mile a second, right? So that's harder. If you look at it in terms of kinetic energy, which is, as you may remember from high school, is half mv squared. In fact, half mv squared, 5 miles a second is 5 times 5, 25 times faster than 1 mile a second. So the energy is even higher than it initially seems. So to go to the moon, we need to accelerate from low Earth orbit to 7 miles a second, which is an interval of only 2 miles a second. So the difficult thing is to get into a kind of parking orbit around the Earth, and maybe then progress the miles on the moon by giving an extra kick, which is a mere 2 miles a second more. But 7 squared is 49, okay? Which is almost double the number of 25. So the kinetic energy you're trying to add is huge. You're going to get it from potential energy in the form of mechanical potential energy in the rocket fuel. So we look at this diagram, which is obviously one I didn't draw myself. And this is a solid rocket motor. And what would happen here is basically ignite it, not that dissimilar from igniting a firework at 5th of November, and it burns out completely until all the fuel is burnt away. You can't stop it. It keeps burning. You can't throttle it. But they are very reliable. They're extremely unlikely to fail. There are no moving parts. And also you can ignite it any time of day or night. So most military missiles will be solid rocket fueled because you can't keep volatile fuels in missiles in the military indefinitely on standby to fire whenever the instant comes when you want to hit a target. So almost all military missiles, things like the Sidewinder missile and so on, will be solid rocket fueled. But there's an upper limit to the energy you can store in solid rocket chemicals, which is what Goddard realized. In fact, Tsiolkovsky, the Russian theoretical space pioneer that preceded Goddard, he already realized this, but he didn't have the technology to build a liquid-propelled rocket. So if you look at this other diagram, which I've also scanned in, with a complicated equation down the bottom, in the propellant, what's referred to as a propellant, is almost always fuel and an oxidizer. The oxidizer is usually liquid oxygen, but you can use other chemicals. So you have to carry both, and for the fuel, you've got options. The theoretical best fuel that you could realistically use is hydrogen, but there are problems with hydrogen. It's an exotic chemical as a liquid in that its temperature is so low, it's not far off liquid helium. It's not that far from absolute zero. It's difficult to store it. It's explosive. It's a very small molecule, can escape through tiny cracks in pumps and so on in insulation. You have to hold it in a kind of thermos flask on the rocket. And until relatively recently, only Americans had ever used liquid hydrogen. But the specific impulse, which is a fundamental thing that tells you how good a rocket is, of liquid hydrogen and liquid oxygen is the highest of all the combinations. But it's technically demanding to use. The Russians never used it in the Soviet era. And because liquid hydrogen has an annoyingly low mass to volume ratio, also known as density, if you had a bucket full of water now, you try to pick it up, you might struggle. It can be a very heavy bucket of water. But a bucket of liquid hydrogen is only 1/7 of the density of liquid water. This is the problem with people trying to run aeroplanes on liquid hydrogen instead of aviation fuel to reduce carbon emissions, because in those designs, for those aircraft, a third of a fuselage is filled with liquid hydrogen fuel. It takes such a huge volume of fuel to cover the distance. Even though the energy stored in liquid hydrogen per unit mass is extremely high, actually higher than aviation fuel. But the problem is the sheer volume of the tanks. Anyway, in recent years, the private sector got involved in space travel. Here's Richard Branson, and the first time I gave in Cambridge, I told a dirty joke about Richard, and I was told I could never come again. He found dirty jokes at universities, so we're not going to do that this time. This is more of a kind of experience thing. This is he had a lot of problems developing it, It flies to a very high altitude, you're technically in space, you can see the curvature of the Earth, it's just a few minutes of zero gravity. It's more I had the experience of going to space, it's not orbital velocity. In fact, it's hugely distant from orbital velocity. If you remember the half mv squared rule, the idea you could just give us a bit more of a kick and get into orbit is naive. But I guess people are spending money on it, first of all they want to do with their life savings they can. So here's a more conventional, very well-known rocket, which is the one the Americans built to go to the moon, which is the Saturn V. The word Saturn V suggests it was a Saturn 1, 2, 3, and 4, in fact there were. One of the things about the Saturn V was the chief designer was Wilhelm von Braun, was also chief designer on the V2. He got him all the way from Germany, and he learned to speak English very well, was very clever, and he then went on to develop this rocket. So, this rocket is in 3 stages. The first stage is kerosene, liquid oxygen. The second and the third is liquid hydrogen, liquid oxygen. The reason is, for kerosene, if the first stage is always bigger than the second is always bigger than the third. So the first stage, were it to be liquid hydrogen, liquid oxygen, you would lose so much in the volume of the tanks, it was so immense, and the weight of the fuselage insulation, that it's not worth it, and kerosene liquid oxygen works out better. So that theoretical gain of hydrogen and oxygen is there, but it's got problems with it. So they compromise with Saturn V, 1 kerosene liquid oxygen, 2 hydrogens. Here's the first stage, with a car to scale, obviously a very big thing. And here's a nice airfix model showing the 3 stages. 2 and 3, getting progressively smaller, liquid hydrogen, liquid oxygen. So there's a kind of rule, in case I forget to say it later, that's kind of relevant to what SpaceX is doing, that basically, in a 2-stage rocket, 80% of the cost is the first stage. So people looking for reusability in spacecraft, if you can just retrieve the first stage, although you haven't necessarily done the second stage, you say, well, you're only halfway there, mate, you get 80% of the money back, especially for commercial launch of satellites. They're now retrieving the first stage, you'll see later on. But this stage, in the 1960s, it was unimaginable they could retrieve the first stage. So the ideal would be a single stage to orbit rocket, it goes into low Earth orbit, deploys a cargo of some sorts, and then lands and comes back to the Earth, goes through the atmosphere and lands somehow, okay? So to explain the difficulty, here's another omniscient diagram by myself. Here it is. This is a 100-ton single-stage to-orbit rocket I've designed. And here is the engine, here's our fuel, liquid hydrogen, which is the best fuel. Here's liquid oxygen tank separate. Here's some kind of fuselage around it. At the very top, here's cargo. So imagine that early diagram when we had rockets getting better and better, 1 mile a second, 3, 5, yeah? If we make this rocket progressively bigger, it will go faster and further at a higher altitude. But will it ever get to orbital velocity in 1 stage? Okay, imagine, hypothetically, we make the actual dry weight of the rocket lighter and lighter and lighter by using carbon fiber, by miniaturizing the electronics, by making the fuel tank out of some kind of fantastically cheap, or not necessarily cheap, but lightweight material, and so on. If you get to the point where the weight of the propellant is more than 90% of the overall takeoff weight, with a dry work less than 10%, then that rocket would go into low Earth orbit in 1 stage. And it's possible that in our lifetime someone will do that as a technology demonstrator. But what have we got left? You've got 10 tons of dry material. In that 10 tons, you've got to have the hull, the fuel tanks, the engine, propellant pumps to transfer the fuel from the engines, some kind of electronic guidance system. You want to come back a heat shield, which is very heavy, parachutes maybe, if you can land by parachute, wings, or you're going to retrieve some food, or you're going to reserve some fuel to do retro rocket firing in SpaceX does to land with that. And make some kind of undercarriage if you're going to land like a space shuttle, and you're going to have any cargo left out of that 10 tons. If you have 1 ton of cargo, you're going to be lucky. Okay? It's very difficult. In particular, coming back is difficult because of all the equipment you need to land with. And that's a compromise that you've had to sacrifice weight or mass that you might have put into cargo. It's almost impossible to do. What happened then was in the 1990s, a group in America, McDonnell Douglas, flew this technology demonstrator, which is was called the Delta Clipper, and it flew to like a few miles high and landed again, and they could actually land this thing vertically on a concrete floor, and there's some video I'm going to show later on of that happening. And then what happened, one of them crashed and blew up, and then they didn't have enough money to build a replacement. But they demonstrated it can be done, and the landing's quite science fiction-like and quite clever. And a lot of the engineers who worked on that were then recruited by Bezos, the Amazon guy, for his company, Blue Origin, and some others were recruited by Musk for SpaceX. So some of these people were young enough to still be around in the industry and had the experience with vertical takeoff and landing and retrieving the vehicle. So this is what happens, each generation of engineers crosses over to the next, and you kind of see what happens. But it was still considered almost impossible to have a reusable rocket. Even just about 20 years ago, I remember reading a statement by ESA saying they had no plans in the next 20 years to build a reusable rocket. So there's another concept here that's kind of difficult to get across. If you look at this rocket engine here, this will be the second or third stage of Ariane. It's kind of long and thin and slender, with a nozzle there at the bottom. If you look at this next picture, here is the first, actually this is a J2 engine, I think, and here is the first stage of Saturn V with Werner von Braun himself standing next to it. So this is looks like a short, stumpy design, yeah? The nozzle diameter is much bigger than its length. And the reason is that when this takes off with kerosene liquid oxygen at ground level, at sea level, the atmosphere is dense. But at higher altitude, the ideal shape for a rocket engine is slender and long. So what you do is you change progressively the shape of the engine nozzle as you ascend by going from 1 to 2, sometimes 3 stages, with each engine being designed to have an optimum size and morphology for the altitude and atmospheric pressure. Here is a space shuttle main engine. Well, the compromise here is they tried to burn the same engine from sea level right into orbit. This is a liquid hydrogen, liquid oxygen engine designed to be reusable. And this engine was said to be 97% efficient. So what had actually happened, they'd almost taken the liquid oxygen, liquid hydrogen engine to its limit by 1979. You could have spent more money and tried to get to 98% efficiency. That'd be a real struggle, and you're not going to get much further. Suggesting we'd taken it as far as you could go, and there's almost no potential for further improvement after that. Here is a space shuttle, in fact, as it was taking off, going through the atmosphere, and it used 2 very large solid rocket motors to propel it in the initial phase, and liquid hydrogen, liquid oxygen in the main phase. So the chemicals coming out of the exhaust here is water vapor. It's H2O is water. We burn hydrogen with oxygen. It's a clean fuel. Hydrogen is a very clean fuel. It's part of the reason people are interested in using it for conventional aviation, because there's no pollution with it. Or cars, in fact, is a fuel cell fuel. You just turn it to water. Here's a solid rocket motor separating, and in the middle you can see the flame of the space shuttle main engine. And it comes back to land. So because we want to land this thing, we've had to put wings on it. There are special ceramic tiles to save it from the heat of re-entry. There's an undercarriage and use some hydraulics to operate it. The crew want to live, so they're at the front, so they need air supply, and so on, okay? And this all adds to the weight. This is weight you could have used for cargo. If you look at this next picture, this is a picture of like an airport where most of us have been to these airports. One thing that does surprise me is just how cheap airline travel is. And I think at the Headley, you can fly across the Atlantic sometimes for less than it costs from London to Sheffield on train. And it's very odd, and part of the way they've done it is the sheer numbers of people travelling. So these aircraft spend 3/4 of their operational lives in the air. You're going to fill every single seat in the plane if you can, and you basically share the money between all the people in the plane. Because there's a few hundred of them, it kind of works. Plus a fantastic efficiency of jet engines at high altitude. So like a wide-body jet flying across the Atlantic uses less fuel per mile than a Ford Mondeo for all people on board the aircraft. It's fantastically efficient using current technology. So you then look at this picture here, which is one of these iconic buildings at Cape Canaveral. The problem here is that launching rockets intermittently. So if you really wanted to have a very low-cost spaceship that like relatively normal people could afford a ticket on, or maybe just to increase the overall activity in outer space, as in science fiction visions of the future usually have. You've got Star Trek. One fundamental theme is you have to have lots of launchers. The same vehicle has to launch many, many times. So if you take 5,000 men in the ground crew to turn the vehicle around once a year, it's going to be expensive, no matter how you do it. Here's a space shuttle being attached to the fuel tank. Obviously lots of men operating this, hard hats. What do we do when it's attached? What do you do then? Do you go on sabbatical? They're still getting paid, probably have some other role. But it was actually more expensive to launch things in the end of the space shuttle than it was using throwaway rockets. It was designed to cut the cost of space travel by reusability. It kind of failed in that aspect. This is another idea they came up with, which was touted a lot of the time, which is something called Shuttle C, or shuttle-derived heavy lift vehicle. So you keep the main fuel tank of the space shuttle, the solid rocket motors, you put 3 engines in the back of a cylinder with just cargo. So the cargo you could then launch with much, much more like a conventional space shuttle, because you aren't bothering with crew, with re-entry equipment, landing equipment, hydraulics, undercarriage, ceramic tiles, it's throwaway. And this would have massively increased the cargo capacity as one mentioned in flight. Here's another idea, which is a difficult concept to get across, but it's really harking back to what I said in the earlier slide. This is what the kind of diagram of a conventional rocket, it's like a bell. And remember, you have a different morphology to the engine with different altitudes. You look for an ideal shape. There's something called the aerospike engine here on the right, diagrammatically, in which you fire the flame without the surrounding nozzle, and you control it using gaseous nitrogen jets to control the shape of the exhaust. Here's a kind of prototype engine in the research lab. It's been looked at for many years. And in theory, the aerospike engine would alter the exhaust shape with different altitudes to give you an idealized thrust, yeah, for different altitudes. I guess you can then start to imagine something like the human iris that changes size with different lighting conditions. Can you build a rocket engine with a nozzle down? Basically, no one's figured out how to do it. It's too difficult to do because of the pressure involved and the forces. But people have looked at aerospike engines. Every so often it comes up. They work quite well in test rigs, but I've not seen one flown for real. So another idea, if you can't build a two-stage or one-stage rocket, you want to go into space anyway, is kind of disguise the first stage as something else and pretend it's in one stage. So here is the X-15, which is quite an old picture now. It's a 1950s aircraft, which people like Neil Armstrong actually did fly before he became an astronaut, go to the moon, that sort of thing, which is a rocket-propelled test aircraft which they just dropped from the inner surface of the bomber and it ignited its engines. Some of these actually flew into space. It's a bit like Richard Branson's aircraft. It doesn't really go into orbit. It was nowhere near orbital capability, but it could fly to the same altitude. And we gained a lot of data from that. Here's one that crashed. The good news is no one was ever killed flying the X-15. They all survived. This one's belly flopped or something in the desert. We landed in the dry salt bed, presumably because the sheer diameter of the salt bed was so big, even if you miss the landing site exactly, you still have somewhere to land. Because like the spaceship, it glided to a landing, so you didn't have any engines to maneuver if you got into trouble. But the holy grail of the whole thing for many years was seen as full reusability. Then in the 1990s, the Americans looked at another idea, another design concept. There's endless design concepts that come out and proposed. It sounds like they're going to build them and then they call them off. Here's one here, which was I think the X-33, I can't remember. This is going to be a single stage to orbit spaceship, like in my hand-drawn beautiful diagram early. It's kind of winged, and it takes off vertically, and then it flies into space. Here's a picture of it in space, and lo and behold, it orbits the Earth and deploys a cargo, that's a satellite or something. I think Venture Star was the other name, X-33, yes. So, but it lands back on the runway like a glider, and they actually got as far as starting to build a 1/3 scale model, see if it would work, and then they abandoned it I think because the people doing the computer kind of simulations of it started to argue that you'd never hit those numbers we talked about earlier, that they couldn't build it all in the minimum possible weight to actually get into orbit. You only need someone to come back to you saying, I can't quite build that girder inside it 4 inches wide, I think it might blow up. Could we make it 5 inches? Someone else says, I want to add a few millimeters to the thickness of the heat shield because I'm worried it might burn up. Somebody else says, alloy, we talked about the very lightweight, we can't quite make it work. But it means the old-fashioned alloy is a bit heavier. Before you know it, there's no room for cargo, or it stops 1% short of orbital velocity. This is a problem. It's on the technology like on the edge of being able to do it. Here's another, I think it's the X-37 project, which was a kind of experimental winged unmanned space shuttle-like vehicle developed by NASA in the 1990s to do, I don't know what, we did look at new technologies in winged space shuttle stuff, and they were going to fly it. They had a budget, they actually had a prototype, and then it was shelved. I guess they must have run out of money, and the Pentagon took over it. And they actually now operate it, it's running orbit now. It takes off in a conventional rocket with the shell around the top, so the actual shape of it doesn't actually have to fly through the atmosphere on the ascent. It's a conventional throwaway rocket. Here it is entering the atmosphere in a diagram built by Boeing, and here it is on a runway. It actually glides to a landing, and here he's surrounded by some guys in the retrieval crew. So somebody stayed in orbit for several years, and because it's run by the Pentagon, they don't just say what he's doing. But some people somewhere are still operating almost routinely a winged, reusable space shuttle-like vehicle. But after the failures of Challenger and Columbia, NASA became fundamentally apprehensive about winged space shuttle-like vehicles. They were worried about loss of another crew. And they went over to almost a kind of Back to the Future thing, looking more at conical spacecraft like the ones in the 1960s that would parachute back to Earth because they were very apprehensive about killing anyone, which they managed to do with 14 astronauts with a space shuttle. Here's another idea. The British had a go at this, led by a guy called Alan Bond, who I met a couple of times. In fact, I was actually interviewed for the design team in northwest of England and didn't do very well in that interview. This is HOTO, which was proposed as a kind of winged space shuttle using a magical kind of engine, which would function like a jet engine on descent, and above a certain altitude, would then switch it over to be a ramjet engine, and as you get higher still, it switches over to be a rocket engine, with the implication that you don't need liquid oxygen in the first part of your ascent. The liquid oxygen is still heavy, but if you cut that out and you use atmospheric oxygen on the initial part of the ascent, you can make that transition to, the numbers add up, you could have a burnout speed of 5 miles a second and still have room for cargo. So the other way to get around the fact that it doesn't quite work is that on the initial takeoff, you have a sledge with wheels on, and a rocket engine's actually on the sledge. So we went to go along the runway, partly augmented by rocket engines on the sledge, separate from the sledge, take off, and then fly. And when it lands, it uses a separate undercarriage to land. But by the time it lands, because 90% of the weight is fuel, it's all gone, the undercarriage is strong enough to hold it up. But that undercarriage wouldn't hold it up on takeoff, it's just too heavy. So you have a kind of disposable or detachable undercarriage from the initial takeoff, which is itself rocket propelled, but it doesn't quite work, right? It's not quite a single stage vehicle, it's so hard to do. It's an artist's impression in flight. Then it got cancelled. It's probably optimistic anyway. They thought about using a Russian Tupolev bomber. He's a wind tunnel test, and saying we could separate it like 30,000 feet, and so that as you separate it from that, you'd already be going at a few miles an hour and a few miles up. They said that might work. I was looked at, but they never took it any further. Here's another concept which maybe is a little bit similar to that, called Pegasus, which has been flying for about 20 years or more now in America. So this is a small orbital launcher. The satellites is a man to scale, and it's not really quite good enough to take off from the Earth and go to orbit. What they did was they put it on the underbelly of a second-hand Boeing 707, took it to high altitude and released it, a bit like that wind tunnel test in the hotel. And you then this falls down, but also a bit like the X-15, yeah? Neil Armstrong's prototype plane that he practiced in. And then the engine ignites and it falls short of the aircraft and it goes to orbit. So what you're doing is you're using the 707 as a kind of reusable first stage. And it's quite cheap and definitely reusable. And you can take off from a conventional looking airfield without all the apprehension of keeping the public at distance and what if it blows up, things like that. And you release it maybe over the desert and maybe even over the sea. So it blows up, it's going to blow up short of the 707, and there's no one there to get worried about it. So that's actually an advantage. Here's a Pegasus in flight. They've launched lots of these, done very well. So a lot of engineers got really frustrated by this whole thing, this whole problem of it's so irritating we can't quite get into space in one stage rocket so that we can bring it back and not have to have separate stages we bring back separately and have to retrieve them from different locations, maybe glue them back together again for the next launch. So we try to think of a way around it. It's similar to the sledge idea of a hotel. This was actually an electromagnetic train, similar to what the Japanese have developed some of their electromagnetic bullet trains. And there's also a German version of that's actually operational in China, which is a magnetically levitated train with something like 400 miles an hour. So what they do is you put your winged spaceship on this train thing, you would rush down the runway or down the train track to several hundred miles an hour and then separate. So that when it ignites its engine, it's already going a few hundred miles an hour. And it just takes, remember that a few hundred miles an hour is nothing compared to 17,000 miles an hour. But maybe that extra kick, it works out the mass, it works to your advantage suddenly, and now you can get into orbit in one stage. Because the chemical energy stored in a rocket is just short of the energy required to be in orbit. It's agonizingly short. That's another computer graphics idea. It's amazing what they come up with. This is 1960s idea, early 70s, which was going to do the same thing. There's a kind of train line that comes up here, but it ascends a mountain, and it separates the ignites its engine with a sledge. It was a sledge concept again on a mountain track, which separated from it, had rockets on it. The advantage then is you can retrieve your first stage, because it's still on the railway track. You just slow down and you gradually bring it back down to ground level and refuel it for your next launch. And they figured that that would just give it an extra kick. So here's a picture actually I put in my Mars tow. The guy I actually met, this is actually Hollywood Boulevard when I was in Los Angeles, and this is a street where famously Julie Roberts picks up Richard Gere in the white, loves the street and Pretty Woman. And these stars they have in the street, it's actually one of the most seedy, dirty, and down-market tourist destinations in the world. And these stars got the names of famous actors, some of them yesterday. This guy's job is to clean them, and he's on his knees, he's got a crutch. And the reason he's got a crutch, he's on his knees, he's actually an amputee. Okay, so he's doing this job, even though he's disabled, which is kind of admirable, a bit of American work ethic there, but it is a bit pathetic. And I don't know how much you're paying for it, just so that we can look at slightly cleaner stars on the floor. It's all a bit crazy. But this guy is quite important to his talk. This man is a taxpayer. And it really is amazing how many people believe that they have a right to take money off this money, taxes, to fund whatever bonkers idea they actually have. Everything from the police, to the civil service, to teachers, university professors, all think this man should give up his money and give it to us, including people who want to spend money to fund some damn fool idealistic crusade to Mars. And they're all convinced they deserve it. If you read an article about somebody who thinks they deserve big government money, they never hesitate, they never think, they have no sympathy or empathy or mercy of any kind for this man. You should give them their money. And unless you can convince people like this that it's worth it, you aren't going to be able to do it. And in the short term, many people like this aren't going to be able to see why we're doing this kind of research. So it is actually been an issue, and you have to acknowledge that not everybody supports you, whatever you do, but it is a problem. You have to be able to demonstrate to the public that it's worthwhile. The ludicrous sums of money spent on space travel in the Apollo era aren't going to come back. Okay, you've got to try to make it work for relatively modest sums of money. Innovative techniques. This is a success of the Portal, which Alan Bond worked on too. It was actually it's recently under controversy and people semi-abandoned and then reborn. And they had a new design for an air-breathing engine called Sept, in this nice picture here. So people are still looking at an air-breathing rocket engine that takes off and then transforms itself into a rocket halfway up, and it lands back on the runway with wings. You can reuse it lots of times. And it's been developed for decades now, because I actually almost did that instead of going to medical school, and they're still at it, and it hasn't flown yet. There are other fundamental concepts. This is a picture of a rocket engine developed in the 1960s, and the peak of spending during the Apollo era, when there's a lot of optimism with then go to Mars. After having done the moon in 1969, by 1979 we'd be on Mars. This is NERVA, nuclear energy for rocket vehicle applications. This is a fission nuclear powered engine. Here's a fission nuclear reactor. Up there is liquid hydrogen in the fuel tank, and here is the exhaust. There is no oxidizer. What you do here is you pump liquid hydrogen past the fantastically hot reactor. You have to fire it up first at super high temperatures. As it goes past the very hot reactor, it heats up. Like if you put drops of water on a frying pan before you put the lard in it, and the drop of water suddenly skids over it. As soon as it hits it, then it evaporates suddenly. Yeah? You run the liquid hydrogen over this very, very hot reactor. The hydrogen gets fantastically hot, it boils over very quickly. That's because it would boil over at like minus 250 degrees anyway. And it becomes a hot gas squirting out the engine. And the specific impulse of this engine is far, far higher, I can't remember the number from the top of my head, than a chemical rocket engine. And in principle, this would take us to Mars or maybe the moon much, much quicker than anything yet imagined. Although exactly how quick depends on what kind of design you're looking at. People yet again, after decades after NERVA was tried and demonstrated in the lab, are looking at nuclear-powered engines again, all over again. You sort of come back involved. It does involve taking uranium into outer space. It's harder than you imagine. Here's a picture of an alarmingly similar picture to the American space shuttle built by the Soviet Union called Buran. This was a Russian copy of the space shuttle. It looks like they copied the orbiter exactly. Kind of naughty. The whole thing looks very similar, but there are a few differences. So on the copying front, I read a paper many years ago in which someone suggested if anybody in the world wanted to make a space shuttle-like vehicle in any country, or like European space shuttle, would be an amalgam of countries, they should be given the blueprints for the space shuttle for free, because we know for a fact that the shape of the space shuttle is okay to land on the runway. It enters the atmosphere, it reaches the runway, it lands. It did it 135 times. Although you might be able to design a better design, this one works, and if you use the same shape next time, you won't spend any money at all on wind tunnel tests or on the airframe design. You can just use the same thing. Maybe make it a carbon fibre or an aluminium, or titanium or an aluminium, but you can use the same shape, which the Russians then do without asking permission. But something else they did, the next picture actually you can see the two together, they are very similar. One of the things that slowed down the space shuttle was the development of a reusable engine. So the Russians made the engines here drop off, and they were disposable. You just retrieve the airframe. So they didn't bother making a reusable engine. They just used disposable engines. It takes you to orbit once, and then you abandon them. Kind of clever. You've got your a bit ahead of the time it would take to make a reusable. I guess you could have phased in a reusable engine later. But shortly after it flew, the Soviet Union collapsed, and it was stuffed. It was abandoned. It's kind of sad. Only flew once. Here, in fact, what they kept flying, which is a Soyuz launcher. Done hundreds of launches. It tends 3 people at the moment in space at a time, and it's extremely reliable. Having said that, 2 have failed and they had to eject the crew capsule. Both times the crew survived. Remember, the space shuttle didn't have an ejection facility. You just blew up. If you blew up, you're dead. So copying this and going back to the future, This is actually the SpaceX capsule, the Dragon capsule, and it is a conical thing, a bit like the 1960s cones the Americans used for manned space flight. And it's kind of sad that we've given up on reusability in a way, but they do reuse this capsule several times. You can get 4 people in. There was an initial design option to get 7 in, but I think it'd be quite cramped. And Dragon is now flying to the International Space Station quite regularly. The cost of launching is phenomenally low. It's almost unbelievable. So some people think the space shuttle cost something idiotic like $500 million a launch, but some people cynically then said it was really more like $1,500 million a launch. Staggering sums of money. Almost like the entire British research and development budget for a year, or half of it, on one launch, depending on what you include in the cost and so on. Whereas this, they were talking about $100 million a launch, so to get a crew into low Earth orbit is much cheaper. But then, they then invoked this reusable first stage. Remember, 80% of the cost of the rocket is the first stage. They started to reuse the first stage. And they actually were doing this for commercial launches like TV satellites and things. It was said to be impossible, as we'll see in a minute, and yet they actually made it happen. They almost went bust a few times, and they did extremely well. Here's another idea that kind of flew in. This is almost the end of the original talk. We've got some video coming in a second. This was something that went back to the rocket or the aeroplane which Steve Austin crashed at the beginning of $6 million man. If you remember that far back, in the opening thing, he's losing altitude, pitches on, I can't hold it, and just crashes. This is a lifting body, which are experimental aircraft which were built. An aeroplane has wings, okay, because it flies in the atmosphere, but to enter the Earth's atmosphere, you need to be stubby and short, and almost flat. Conical is the ideal shape. So we kept altering the design to create a compromise which would minimise the wings, and the lift through the atmosphere when you came into land would be developed by the airflow over the entire fuselage rather than the wings. It's called a lifting body. The lift was derived from the body. And lots of experiments dropping them from high altitude, and then they abandoned that. Some of the technology was put into the space shuttle, and then someone got it off the shelf, and they tried to make a kind of cheap shuttle replacement, and that's actually now called Sierra Nevada is a company which now operates that. It's been on standby to launch unmanned for the last year or two. There's been some delays to it. These things often agonizingly delayed. Here's another bonkers idea which was abandoned, which was during the landing. It would actually deploy some rotor blades like the helicopters that came into land. The rotor blades would spin in the atmosphere like a wind as it descended and generate lift like helicopter rotor blades and slow it down. Then you had a controlled landing without parachutes, so you could land with some degree of control. They ran out of money and that was abandoned. Kind of interesting idea. So, there's a new innovation for Kut's talk. If I can get it to work, I've actually got. I can make it work. Hang on a sec, guys. Should have to do this.
You were very close.
Yes.
You see cursor?
Yeah.
Oh, yeah. It works better on the screen. It doesn't like computer.
That's it.
Yes.
Here we go. So this is the DCX with an audio. So this was an experimental device, a scale model of something that it wasn't big enough to go into orbit in the 1990s. Here it is taking off. In fact, I ought to have edited this a bit more. It spends some time in mid-air flying. There it is flying away with reusable rockets. They did all kinds of clever things to make it for almost no money. They used a guidance system which you borrowed from a fighter jet rather than developing an original bespoke system. And they used some off-the-shelf technologies to demonstrate that they could do it for almost nothing. And here it is coming to the top of its 10,000 feet is the maximum altitude, which is about 3 kilometers. So it's only technology demonstrated, it's nowhere near. Here it is maneuvering. Amazing versatility. It's coming down. Let's see if it can land. There you go.
That is clever.
So for example, as God and Robert Heinlein intended. So it was actually, the idea here was there's 15 crew launching it, as you said, and it's obviously a scale model, and the space shuttle at the time required thousands of men. There's a bit in a few seconds, might as well show. It's obviously only a scale model, this wouldn't be big enough to go into orbit. There's just a good bit at the very end, it's worth watching. Here we go. Another successful landing. Hooray! Retro rockets firing. Legs deployed. Great! Engines out. Not so good. And they didn't have enough money to build a replacement, so that was the end of that one. Okay, so there's 2 or 3 more videos that are worth watching. So basically, to summarise, the booster is 80% of the cost of the rocket. If you can retrieve the first stage and not the second, which is what they're doing with the satellite launcher, then there was originally a plan to use the first stage 10 times without major refurbishment. They've now taken it to 20. So they're coy about exactly how much it's costing, but SpaceX, a company which some people thought wasn't any use, has captured 80% of the satellite launches in the world, and is launching more than 2 launches per week. Okay, the engines, about 75% of the cost of each stage. So if you just retrieve the engines, you get a lot of the money back. You can use them again. So there's all kinds of ideas. Some of it being with but the engine will separate from the main rockets, about parachute back, and it's too hard to retrieve the whole thing, but maybe I could get the engines back. So the Starship, which is a big rocket that they're launching at the moment, keeps blowing up, but they say they're getting there, that would take in its reusable form 100 tons to orbit, which is similar to the Saturn V. But if the second stage is abandoned, and you've got a second stage disposable, as they do with the current satellite launcher, you can get 200 tons because you're wasting 100 tons on the heat shield, on the landing equipment, on the fuel you're holding in reserve to land with, and so on. Yeah? And you have to be a bit strong if you're going to use it many times. So some people think they can't get that second stage to work, the Starship, they may just go for a disposable version. Here's a bit which, again, I don't know if this is going to work, so it may not be loud enough for you guys to hear. If necessary, I'll be like a ventriloquist. So you're not going to be able to hear it too far out, okay? What this guy's saying, unfortunately, is British. This is 2013, it is 12 years ago. He's being interviewed about, are you worried about SpaceX? He's working for Ariane Space and the European Space Agency. And what he's saying is just too quiet for you to hear. I was hoping you'd be able to hear it. What it's saying is, SpaceX are selling a dream. It's not going to work. They can't make it work. He lampoons them a bit, and he says, what you do to someone having a dream, you don't wake them up. Okay, he dismisses the idea of reusability. But he's really got any space now, because in fact, they're reusing the first stages 20 times. Okay. Okay, let's see if we can get this thing to work as well. Oh yeah, there you go. So here's a view from the first stage, coming into land, into the atmosphere, some clouds, retro rockets firing, here's a drone ship, and it's landed. So you landed in the Atlantic, you go up, altitude, maybe, and then you go over the Atlantic on a drone ship, which you put in that place, people on it, because it blows up and kills everybody. Here's, let's look at the better one. So here is the latest one they've got, which is the Starship thing. He was ticking off. So the propellant for the Starship is liquid methane and liquid oxygen, okay, not hydrogen. Slightly lower specific impulse. It's easy to handle liquid methane because the temperature, when it's cold, it's nowhere near the very cold temperatures of liquid hydrogen. And it takes off, here it is. These things on the upper stage, these are really for landing. You don't really need them to take off with. So if you use a disposable second stage, you get rid of the fins, which you've got to weigh some more weight, yeah? The electronics and mechanical devices operating the fins. And there's also the second stage covered in these tiles. You can see a bit like the space shuttle, a bit of ceramics, which are going to be carefully manufactured. There is a problem getting, as there was with the space shuttle, getting the glue on. So what just happened is the second stage is separated from the first stage. The very first test flight, it didn't separate. They're a bit shocked they couldn't even do that at the time, but there you go. Test flights are like that. SpaceX have a relaxed attitude to catastrophe. They blow up a lot of rockets as they learn along the way, and some space companies would have been alarmed by this, but they've just kind of accepted it. And it's almost inspirational for your own life. You copy, what the hell does it matter? I'll just alter my design and learn from my mistakes, and next week I'll do better. So here's the Super Heavy launch vehicle, which is an immense thing, coming in with all its engines, and it's trying to land like we did earlier on it's not a drone ship. How can we land this? And how can we save a weight of those expensive and heavy hydraulic landing legs that come out and deploy as you're about to land, as Robert Heinlein would have had it? Here it is, ignition. So that by now, it will weigh like probably about 10% of its takeoff weight, so it's overweighted takeoff as fuel. It doesn't really weigh anything now, except obviously it would push you to death if you got near it, but it's nowhere near as heavy as when it took off. Here's some people watching. First time I saw this, I must admit I was impressed. Here it's coming in. I thought this was, when they suggested this, I was in the same mood as that guy from ESA 13 years ago, and I said, you're not going to get it up to work. I thought maybe they'd try 20 times to make it work once, and the first attempt, they caught it. So they catch it with the two fins, with two arms that fold in. So you've got to land within plus or minus 2 or 3 feet of a location a few thousand miles from where you were at maximum height. It's extraordinary. I honestly thought they couldn't do it. But the people in mission control were out a bit of a fit. They can't believe it. There was a bit more film. What's this? Oh yeah, this is the second stage. So at the moment they're doing some orbital flights over the fire of the Atlantic and Africa and land in the Indian Ocean. Here's the second stage, and the actual return of the signal is much, much better than traditionally. And you've actually got a picture there of the ionizing gas around the spaceship as it enters the atmosphere, which you've never really seen before. Here it is coming to land, second stage, fragments of extra rockets. Obviously, ultimately, you do it in a pre-prepared location, try to catch it, all these landing legs. It's landing there in the sea. So that they have a buoy, a small like life raft size thing with a camcorder on it, something that just records the landing. And we've got here. Here we go. This is the most recent flight, which was the 10th flight. So quite a lot of them failed, and people started to question whether it was really viable. Quite a lot of critics have said that it's impossible. It is extremely difficult. Here we go, landing in daylight this time in the sea. Some of the tiles actually fallen off. That's actually a problem they've got. So what they're talking about doing is launching one and landing it and taking off the same day. Is that a different picture? I can't remember what this one actually. Oh yeah, so this is where it gets more complicated. Supposing you want to go to the moon, okay, which is what it's all about, or Mars. He's saying this Starship thing is the ship will take us all the way to Mars, and it will actually land on Mars and take off again. The problem is, when it gets into low Earth orbit, there is no fuel left. All the fuel is completely burnt out 250 miles up. Then we have some cargo. They talk about launching a space station into a low Earth orbit. But the idea of going to the moon on Mars is another question. But they then say, that doesn't matter. We'll launch the spaceship into orbit, then we launch a second one. Instead of cargo at the front, we will have methane. Plug it into this spaceship here. It's actually docking. It's like two blue whales mating in orbit. And then we transfer the methane over. Then we launch another one with liquid oxygen a few hours later, and we transfer that over too. To get to the moon, here is the second stage now, full of fuel, is off to the moon, okay? There it goes. To get to the moon, you might have to launch 10 or 15 Starship rockets with like 10 or 13 of them just as fuel tankers to get one machine on the surface of the moon, which at first sight sounds optimistic. I must admit, it's hugely optimistic. But SpaceX have pulled off miracles before. It's extraordinary what we've accomplished. And my thought, like when I first wrote this more than 10 years ago, was kind of somber, saying, you know, nothing's really working. The true cost of space travel has little changed since the days of President Kennedy. It's only a few things are really advanced. But SpaceX have brought in reusability and have really taken over the whole market. No one can really compete. There are bizarre alternative strategies, like for example in India, they've now developed quite a convincing rocket launch program, and the wages in India are so low that you can actually make them for very low cost. Something along you could just subcontract some of the rocket launches to India, and it would make them at much lower cost than making these American engineers. Much the same way that iPhones are made in India, yeah, rather than America. They said recently with Trump's idea of bringing manufacturing back, an iPhone will be 4 times more expensive if you make it in America than if you make it in the Far East. So somebody said, why not make rocket launch vehicles in the Far East too? Controversial. But if it can make Starship work, the cost of space travel will plummet, which is what they'd always anticipated to literally just a few percent of what it was. Remember that more than 90% of the cost of a launch, so actually maybe I should have got that wrong actually. Only 1% of the cost of a launch is fuel. Okay, if you retrieve a rocket again and again, the cost will plummet. The costs were high because you threw away the entire vehicle every time you used it. The problem with the space shuttle, it took so much effort to refurbish and reassemble it when it landed, and bits were disposable, that it never really achieved its objective of reducing costs. It's actually more expensive using throwaway rockets. But maybe they're finally getting there. And also, there's other private companies. Bezos, the Amazon guy. If you're a super rich billionaire, you've got to have there's a hobby, a rocket company. And a few other people, like I guess Richard Branson with his thing. There's 2 or 3 other players coming in, the group called Rocket Lab, and they're all looking at reusability and maybe innovative new ways to do the whole thing haven't been thought about. I think it's partly because Lockheed Martin, Boeing, if you look at their rocket division, something like the average age of their engineers is 53, whereas at SpaceX, a lot of them were in the early 20s and mid-20s. And if you'd ask someone, I think at Boeing or Lockheed Martin, can you do a reusable rocket? They said, we've already looked at that, we can't do it. Okay, we kind of set in their ways. They'd already been proven you couldn't do it. They got a younger generation of people who just did it. And it seems to be working quite well for them. So that is, I think, at long last, unless I've got another slide in reserve. Here we go. Here's a nice line from the Russian space pioneer, which is translated differently depending on which translation you read. The Earth is the cradle of reason, but man cannot stay in the cradle forever. So the Kovsky predicted, even before World War I, predicted the advent of a space-based economy and industry and colonization. Still unfulfilled, but people working on it. That's the end of the talk. Questions?
Right, so who have we got for the first question?
Oh yeah, go on, yeah.
We've got a...
How would they
Hold on,
think of getting
let's just
someone to
read.
Mars under what you've just been
Oh,
saying?
what, sorry?
Would you think of getting someone to Mars?
You're a Starship. You're a Starship to Mars?
Yes.
Yeah, so it's designed to do that. You basically, so to break Earth orbit, you get 7 miles a second, that's your escape velocity. It's the same for the Moon as for Mars, but Mars is over 100 million miles, the Moon's only 250,000. So the Moon's just a couple of days to get there, whereas Mars will be several months, 7 months say. There are people looking at nuclear propulsion that might cut the journey to like 3 months or 4 months, which would be extremely good for all kinds of reasons. But it's not pie in the sky, it's still in development. So it's designed to go to Mars, and Musk keeps talking about it all the time, but it's the same thing, the same vehicle would land on the Moon or Mars. It would take longer to get there. You have to refuel it in orbit.
Okay.
Yeah. Thank you. Terrific talk, and I too thought about the Mars problem, so I googled it. Manned trip to Mars.
Yes.
It said in the order of money cost 100 billion to $1 trillion.
Yes.
I think that's a bit of a job stopper, even for Bezos and
Musk.
the other
So I
guy.
agree. The only thing is I think in the end they're only going to do it if you had some phenomenally emotive reason, like when the Americans felt overshadowed by the Russians with Sputnik, emotive reason to justify, or if it can dramatically reduce the cost of launches. So that figure will have to be reduced to something less than 10% of that, maybe even the 5% of that, to have a realistic chance of going to Mars.
Yeah.
Even this return to the Moon is proving very difficult to do, because there's several groups now trying to go back to the Moon. You get 3 or 4 people back on the Moon with all the technological advances we have since 1969, and they're struggling. Okay, they keep changing their plans, redesigning the ship. The Chinese may get there before the Russians, also before the Americans. Even the Moon is difficult to get to.
I'm having a terrible problem with the physics of it all.
The physics is straightforward. It's more of an economic cost, and also it's also about whether the human body could withstand the journey. That's a separate issue.
Yeah.
Right.
Okay.
Right then.
Thank you, Stephen, for a fantastic talk. About halfway through, you were talking about a hydrogen engine that was effectively vaporising
Nuclear engine, yes.
over the nuclear.
Yeah.
Because we're not actually oxidising that hydrogen, why wasn't something more efficient than hydrogen considered? CH4 and then 2?
Right, so in the Arthur C. Clarke novel, I've got my own microphone, the Arthur C. Clarke novel, where he actually talks about that, obviously he was a theoretician, a science fiction writer, he was quite clever, and he said they're using methane rather than hydrogen. I think it was actually 2001 Space Odyssey. In his design, he said it was a fission reactor, pumping methane past it, so it's easy to keep it as a liquid. But in that experimental thing was hydrogen. I think hydrogen still has the best performance in that scenario, I think.
Okay.
I'm not actually sure. I'm sure you could use something else.
There were so many different orderings going in my mind, because to contain hydrogen you need something much stronger. No, stronger is the wrong
Tighter,
word.
it's tighter. It's tighter.
Thank you, that's the word.
Yeah.
So
But that's the problem with these helium-filled and hydrogen-filled airships. I think you're bringing those back.
bigger molecules,
It
because
just
they're
leaks.
heavier.
It really just leaks. You have to build a membrane which was impermeable on an industrial scale.
Yeah.
And there's apprehension about leakage because the molecules are so small.
And just while I'm still there, a very, very quick one. Right at the start, you're talking about solid fuel and saying you can't start or stop it.
Yeah.
Lots of little compartments, not worth it, not feasible.
Yeah, so when they go from low Earth orbit to geostationary orbit, you do two separate burns.
Yes.
What we have is a perigee engine burn and an apogee engine burn. So you convert to a circular orbit to an elliptical orbit.
That makes
And at
sense.
the apogee, which is at the same altitude as the geostationary orbit, you fire a second engine. But you can't switch them on and off, so you have two separate engines stacked one behind the other. So you throw the first engine away as you leave low Earth orbit, and the very top of the ellipse, you fire a second engine.
And he's smaller.
And yeah, it's smaller, and that would just circularize the orbit at that altitude.
Thank you
But
very
because
much.
it's solid, you can't switch it on and off. So
No,
if it was liquid, you could turn it on and off. Yeah.
Indeed, thank you.
Question over there.
John Lowe, Museum of Power. You talked a little bit about, I'm up here.
Oh, sorry. Yeah, right.
Okay, microphone doesn't help. You talked a little bit about money and business and how it flows in the States. Could you give us a quick thumbnail view of what you see as the prospects for Europe or for UK in particular being successful in this business?
God, right, it's not easy. So the idea of the British, or the talk of ESA joining that project which Alan Bond started for like a winged space shuttle hotel, and then it became the Satan driven thing, that may yet get there. They just haven't got there yet, okay? I don't know how far off they really are. They've made like amazing progress, but to have a viral machine that would fly, I don't know. We haven't even got a prototype that goes to high altitude. There is potential for using that kind of technology in like a sequel to the Blackbird spy plane. So you go Mach 5 at very high altitude, in which case you could sell the engine to the military and they would pay for it. That's actually an option, but not quite orbital velocity. It looks like, if Starship was really, really successful as they claim it might be, it may be that all launches would simply be done by SpaceX, and people, because it's so much more effective than, say, Ariane, which is a European launch vehicle. But you don't know. I mean, been lots of false dawns before. There's always optimistic talking in space travel. He was a little kid reading books in the 1970s. There was talk about how amazing things were about to happen any minute, and it's often disappointing. There's often setbacks and things are abandoned and projects aren't completed. The space shuttle had a lot of technological euphoria associated with it when it first was about to fly, and then it didn't really live up to expectations. It did fly, but it wasn't as good as they hoped it would be. So with SpaceX, what Musk has got is that very low altitude satellite thing called a constellation satellites. We have several thousand satellites at low Earth orbit. So wherever you are, any time of day or night, there's always one satellite going overhead. And you could basically have internet connection with broadband to this system, and you pay something like $50 a month to get the privilege. And you could do this even if you haven't got open reach to go to your house. You could do this in the middle of Africa. You don't need to have a fibre optic link to your house. And you pay something $50. But if you've then got 100 million people sign up to it around the world, you've now got an immense sum of money coming in, $5,000 million a year from 100 million people. So we're hoping for like $12 billion a year just from Starlink, basically using the internet connection to generate money for them. And most of the SpaceX launches at the moment are launching Starlink satellites. I honestly don't know how realistic it really is. It must be realistic, but they're obviously very, very clever. They couldn't do all this. They must have a business strategy that thinks they'll make money out of it. But the point you're making here, that it's never ever going to work unless they can reduce the cost immensely. But even if you cut the cost to 10% of current cost rather, in the same way that maybe the Dragon capsule is less than 10% of space shuttle, it's still much too expensive for the average person to afford. It's still, like, if you put 7 people in the capsule and you launch it for $70 million, that's $10 million each, about £7 million each. It's extremely difficult. Remember when the Americans deployed men in Afghanistan, the cost for 1 year to put one soldier on the ground for 1 year in Afghanistan was $1 million per man. That was the logistical cost of keeping a soldier on the ground in Afghanistan for 1 year. And they had something like 150,000 men on the ground at one stage. So they have got great resources, but it still would be something you'd only do on a relatively small scale with a few super clever, carefully selected, people going to orbit to do clever things. You want to make it much more affordable as airline travel has become. You need fundamental improvements. I'm not saying it's impossible, it's entirely possible, they're just not there yet. Europe, Europe hasn't been, that guy there in that video didn't believe they could do it. But now that the Americans have demonstrated you can relaunch, reuse these rockets, surely somebody else will copy them quite quickly, just like everything else is copied, yeah? Now they've demonstrated you can do it, it will be copied, just like China is now copying Western technology and becoming advanced power. Not many of their ideas are entirely original, they're just copying what's already been done and maybe developing it further. So once psychologically you realise you can do it, then they do it. So one of the other talks I've got a picture of guys at the top of Mount Everest with oxygen cylinders, because they thought you need oxygen to get to the top of Mount Everest. And you had people, Sherpas carrying cylinders to certain altitudes, and you'd leave them in the pile, and the guy would get there and then change his cylinder so he could still breathe. But now, about 300 people a day climb Mount Everest, costing about £20,000 an adventure holiday, and they're breathing air, okay? There's a psychological barrier. And these are relatively normal people. They aren't very collected, very carefully selected, super fit army people who can climb mountains. Relatively normal people climbing on air. You can't run very fast at that altitude, but you can survive. There's a psychological barrier. They thought we needed oxygen. So it may be that now the psychological barrier of saying you can't retrieve a rocket and reuse it has been broken. Maybe other companies will do it quite quickly and maybe overtake SpaceX. We don't know. Bezos is trying, yeah? Bezos is behind. Yeah?
You mentioned different types of fuel and oxidizer combinations.
Yeah, there's lots of them, yeah.
What's the state of research into entirely different types of propulsion?
Right. So basically, chemists can tell you how much energy there is in different chemicals relatively easy you can combine. The standard one is kerosene. Kerosene is oxygen. Well, at the end of the Cold War, the Russians, it turned out in secret, had a different kind of, I can't remember how it works, a kerosene liquid oxygen engine. It was significantly more efficient than was previously thought possible. It's something to do with, cows vomit their food and chew the cud and swallow again. They did it twice. It somehow burnt the fuel twice in 2 chambers. And they got more thrust out of it. And the Americans actually bought a couple of hundred of these engines and actually put them in the United Launch Alliance rockets. They were so good. There's some problems now because they're falling out with Russia, you can't get any more. But there was some advance with that. So kerosene liquid oxygen does work, and it's reliable, and it's relatively unsophisticated, especially for the first stage of the rockets. But the idea that some other chemical combination we just haven't tried yet that would work better, it just isn't possible. There are only 90-something elements in the universe.
Is there something beyond the idea of burning 2 components?
In terms of chemical, yeah. In terms of chemical reactions, there's like an upper limit to what you get. In the 1950s, when people were very keen on nuclear power, they said nuclear power would be too cheap to meter. In fact, that didn't happen, right? But we do have nuclear power. But like 1 kilogram of uranium has got like as much energy as like, a million tons of coal. Because the chemical energy stored in coal, which when you burn a piece of coal seems quite hot, is nothing compared to the potential of nuclear physics. It's just there are other problems with nuclear physics apart from the fact that it's a lot of energy in a small space. But the actual theoretical energy stored in a nuclear system is much, much better. But it's not easy to transfer that energy rapidly into, say, propulsion. There are different approaches to it. Certainly not there isn't any plans at all for nuclear-powered rocket to launch from the surface of the Earth. It would be like a 3rd stage. You ignite it in orbit. You take it up with a conventional rocket to orbit around the Earth, and then you'd ignite the 3rd stage with a nuclear engine in orbit. And then that would give you some fantastic burnout velocity on the way to Mars, say, or Jupiter.
But what if the debris came back to Earth?
That's been looked at because, for example, some of the Mars probes on the Mars now are using plutonium. There's like a football, so it's maybe like a tennis ball sized piece of plutonium that generates electricity to drive around Mars with. And during the launch, if it had crashed, it'd have been stuffed. But I think they must have found a way to put it in some box that would survive the explosion, because quite a few satellites have used radioactive material in them, and so far I don't think there's scattered one everywhere. It must be something like the black box they have in flight recorders, so that they think they would survive the explosion. But yeah, it is worrying. It is worrying that they're launching fissile material over the ocean. It would be difficult to retrieve it, blow up.
The question coming here?
Looking
Am I-
into a possibly
Yes.
distant future,
Yes.
do you think there's any possibility that we could accelerate rockets to relativistic speeds using
Yeah.
Can you repeat that?
Relativistic velocity, like close to light speed. What happens is that it's a bit complicated. It's according to current theoretical physics knowledge, it's fundamentally impossible to go at the speed of light. As you accelerate, you get close, in fact your mass increases. In fact, at light speed you would have infinite mass. You could get maybe halfway there. There was one of these BIS projects, British theoretical group, had a theoretical design for a kind of nuclear fusion powered thing, and the mainstay, like half a mile wide. They could get to Barnett star in something like 20 years. We've got 10% of the speed of light, I think, as its burnout speed. That was nuclear fusion powered. They thought that, in principle, using the energy you'd have from nuclear fusion fuel, you could reach 10% of the light speed. But even that's a lot. 10% of light speed is fantastically high.
No way.
No way? It's called Daedalus or something. Go on Google.
They can call it what they like, but you can't get nuclear fusion to work on the surface of the Earth.
Not at the
never
moment,
mind.
no. That was a theoretical study for the future. So in fact,
No,
last
sorry,
year,
it's a no-no. There's a
last year in America, for the first time ever, a nuclear fusion research lab achieved gain. Okay, no one's ever done it before. They got incrementally more energy out of the pellet than they put in. So what technique did they use? You know what they used? Lasers. Okay, they had a pellet of fissile material, and they hit it with lasers from several directions at once, and the energy put in was slightly less than what they got out, so fusion was occurring. So fusion was demonstrated by Rutherford before World War II, but the energy you get out is less than what you're putting in. So if you ever get more, it's called gain, and so far no one's achieved gain except the laser thing. So the Daedalus project idea was to release the fuel as pellets into a combustion chamber and fire lasers from several directions at it, and they would explode as a miniature fusion H-bomb, and the explosion would propel the rocket forward in tiny impulses over several years. So they worked out the energy you then get from a fusion reaction, if you can make it work, and they worked out how much fuel you'd have in the thing, and then what the burnout velocity would be. Go on Google. I mean, it's not, you couldn't build it today, but I'm not saying you could never build it. That's more like theoretical physics diagram with a pencil and a piece of paper. Not actually, no one's actually anywhere near building a nuclear fusion propelled rocket will get to Barnett star in 20 years or something. No one's near that.
I think. Okay.
Go on, I'll tell you what the key words are. On Google, it's DIS, British Interplanetary Society.
Right.
And I think it's Daedalus.
Okay.
And Alan Bond was one of the scientists involved in that. He looked at that.
Thank you.
Yeah.
Yeah, I have a couple of questions actually. So the first one, now many people have many different opinions about this one, but what is the biggest problem with atomic engines?
Right, so the biggest problem with the different kinds of atomic engines, okay? So we also just talked then about different kinds of nuclear power. There's fission, which is like uranium, in which big atoms are persuaded to disintegrate, and that creates energy. There's also fusion, in which very, very tiny atoms are glued together to make bigger ones, okay? The ideal atom in physics is, anyone know? Iron. Iron is the atom with the lowest internal energy. So all atoms secretly want to become iron. So if you're smaller than iron, you want to glue to another atom to get bigger. And if you're bigger than iron, you want to disintegrate to small atoms to become iron. That's what it's all about. I want to be iron so much. So what we usually do is try to fuse hydrogen together to make helium. So it's just been said, there's been over 150 projects around the world to try to make fusion work. But they claim they're on the edge of making it work, but they still can't quite make it work. Right? It's actually better than fission. All the reactors in this country, like Sizewell B, are all fission. This new nuclear sea project is fission, using like uranium. But in principle, maybe soon, they may have fusion working. There's several groups working on it. An American group claims to be on the edge of it. Chinese claim to be on the edge of it. There's a new project called ITER, an immense cost being built in the south of France with like 10 countries involved. There's another fusion reactor, but they can't make it work. But that doesn't mean we'll never make it work. If you look at what we can do, which is nuclear fission, okay, how are we going to use that to power a rocket? Which has just been said, there's a danger in launching the material into orbit because it's radioactive. What if it blows up and scatters everywhere? How the hell are you going to retrieve it? Are you going to poison the ocean? It's a very big worry. People worry about it quite a lot. But imagine you stop worrying about that and just going to do it anyway. The ways to do it, you can use a nuclear reactor to make electricity in orbit, with an immense amount of electricity over a protracted period of time from a nuclear reactor, in the same way that, at least in principle, fission reactors create more energy than 1 million tons of coal, yeah? So, you then make this electricity, how are you going to turn that into propulsion? You use an ion drive, in which the energy, it's electric propulsion. The energy for the ion drive is derived from the nuclear electric energy source on board. So you accelerate a gas in an ionized form, similar to a particle accelerator, and it shoots out the thrust comes out the engine at fabulously high speeds, many, many times faster than kerosene, liquid oxygen, or hydrogen oxygen. And this gives you a final burnout velocity of something potentially fantastically high. So the vogue in Europe today, say for telecommunication satellites, which occasionally have to adjust their position, is electric propulsion, ion drive. But the energy source would be solar electric, with photovoltaic panels in the satellite, the electricity source to fire the engines. For the moment, they're still using mostly chemical. It's actually nitrogen tetroxide and some kind of inflammable propellant mixed with it. You can use nitrogen tetroxide as an oxidizer other than oxygen, but it doesn't work as well. But it's easy to contain because it's a liquid at room temperature. So you can, at the moment, it's using chemical, there's a vogue drifting towards ion drive with the electricity source being solar power. But in principle, you could use the nuclear reactor to make the electricity and use that to drive your ion drive. However, the other philosophy is to use a reactor to get very, very hot, which that's what we do. These reactors, it's weird, it's just a lump of material which you persuade to get fabulously hot by nuclear reactions. And you actually put your hands in it, it would feel very hot, in fact, you burn your hands off. And when you use it to heat something else, so in that design we had earlier, NERVA, you pump the liquid hydrogen past it. There is a problem when the hydrogen first hits it, it's super cold, and the first bit of rod it hits will maybe be so brittle that it might actually snap. But then further down, as the hydrogen continues its journey, there'll be temperature gradient effectively along the length of the reactor. That's actually something they worry about in terms of the dynamics of it. But you could use that to accelerate your hydrogen with no actual combustion. So your energy source, your kinetic energy, and your half mv squared, is ultimately the energy derived from the reactor, and you can store astronomical amounts of energy in a nuclear reactor compared to any known chemical combination. The whole philosophy, remember when nuclear power first came in, that said, we cracked the whole energy crisis, we use nuclear power. But there are problems in using nuclear power, which many people in the audience will know about, as a source of energy on the Earth. And there's also anxiety about using it in space. There's several very advanced projects right now, including one in Britain. For a small nuclear reactor, you could use the moon as the energy source for electricity, so the astronauts have electricity all around the lunar cycle. Remember, on the moon, you'd have 15 days of daylight and 15 days of dark. So you couldn't use solar power unless you had some kind of battery to store the power from the sun. In daylight, it'd be fine, you have terrific energy. But it's 14 days is a long time to go without any energy in extreme cold of the moon. So we're talking about having a small reactor, so smaller than a motorbike or something, or a telephone box that would provide the energy to the moon base. There's several groups looking at those now. There's even groups looking at using those to power a data center. Nuclear reactors the size of a car or something that they'll plug into a data center, because there's a lot of anxiety in data centers use so much electricity, the grid can't cope with it. The Americans are looking at building small modular reactors to power those. But fundamentally using fission nuclear reaction energy. Okay, well, we could translate that into space travel by basically the two options are ion drive, which is essentially electric propulsion using a nuclear energy source, or nuclear reactor to generate heat to heat up, say, liquid hydrogen, or you could use methane, or almost any chemical, if you pumped it past a reactor, would get very hot quite quickly, increase its pressure and squirt out the exhaust nozzle at some fantastically high speed, and it would propel you forward. And your burnout velocity would be much, much higher than any conceivable chemical combination. It's not yet being done in outer space. Refueling a rocket, like the military routinely refuel their aircraft at high altitude on missions from a tanker, that's never been done in low Earth orbit in zero gravity. There are lots of fundamental anxieties about whether we can even do it. Not so you can never do it, and it might be something that takes 20 years to perfect. And the whole SpaceX plan to go back to the moon is critically dependent on transferring liquid fuel and liquid oxygen in zero gravity at 250 miles up between two vehicles the size of a super yacht.
Did you have the second part?
Yeah. So it's not related to this, but I don't blame anyone here if they haven't heard of this paper. It's very recent and it hasn't blown up or anything. So there's this thing about quantum space tension, I think, where they use liquid helium for a gyro. So let's if you have heard of it, why are they using it in present rockets? It's way better than the one they use now.
I don't know, I've not heard of it, no. Who's using that?
Huh?
Who's using that?
No one has started using it. It's just a hypothesis.
It sounds like a kind of thought experiment, blackboard, future, long-term future studies thing. A bit like the Daedalus planet with the Barnett star, yeah? We're decades away from being able to build it, but if you do the fundamental physics, they think they can make it work, but you sort of believe it when you see it. Doesn't mean they'll never do it. Think about the idiot who made a fool of himself saying SpaceX couldn't reuse a rocket.
Yeah, and my third question is, could we lower the AC? It's chilly in here.
Yeah, we haven't had any from this third of the audience.
No.
First, the apology. I haven't actually read your science fiction book.
Damn.
Oh, sorry. By now that I know it exists, I'll give it a
Have a go.
How did you get your people to Mars?
It was a chemical rocket. Chemical rocket.
So, you know the propellant, and you said one of them is close to absolute zero.
Hydrogen, yeah.
Yeah, how do they keep the propellant so cold and in liquid form when the engine gets so hot?
Good question. Right, so the tank is separate from the engine. You know, the petrol in your car would blow up if it was near the engine at engine temperature. They keep it separate with a pipe underneath the vehicle and then where you sit. So the engine's at the opposite end of the vehicle to the petrol tank. Yeah. So they separate them as pipes running between them. But the temperature in the engine will be immense, and then there are pumps that pump the liquid down. It is a problem of restart in zero gravity because the fuel inside the tank, if it's all half empty, the globule of fuel might float to the top and not near the holes for the pump. So it's actually quite difficult, but it can be done. It's basically a thermos flask. Yeah, it's a thermos flask. So the temperature, I can't remember what it is for, if you look it up on Google, that seems zero, I can't remember, 273 or something, and then, so then a bit after that is helium. Helium is just a few degrees, which we use in MRI machines, just a few degrees hotter than absolute zero. And then just a few degrees hotter than that's liquid hydrogen. It's almost the kind of temperatures that you'd associate with an experimental physics lab and not almost a piece of industrialized equipment on a massive scale being used every day. And yet that's what we're now trying to do. We're trying to use liquid hydrogen for aviation, which is, or even, maybe even for cars and fuel cells. Yeah?
Thank you. Really good speech also.
Right.
I think we'll take one more after you.
Yeah, the last question prompted this one. My son did some work on MRI scanners, which use liquid.
Yes, yeah.
And apart from the heat, the energy needed to boil the helium is very small.
Yeah, you incrementally go to the lower temperature to boil off.
So, just some vibrations are enough to
Yeah.
make them purge. So how do they deal with the vibrations, or
Well,
is hydrogen so much further away from helium?
I can't remember how much hotter it is. I saw them as recently. I could remember absolute zero then, couldn't I? But it's just a few degrees. It's not much hotter, but you can keep it as a liquid. But it's harder than aviation fuel or liquid methane. Yeah. So I think the hydrogen fuel cell car ideas are mostly based on like an aqualung-like cylinder full of gaseous hydrogen at high pressure. I don't think many people suggesting liquid hydrogen in a car down a motorway. They're talking about hydrogen that would be filled as a gas.
Yep.
Like an air cylinder, like for an aqualung, or an oxygen tank in a hospital, for portable use. And you'd fill that with hydrogen, and then you'd metabolize that with atmospheric oxygen to make electricity. That's
Yes.
been looked at as an alternative to battery-powered cars.
But you forgot about the catalyst they need, and there's very little platinum,
On planet.
and that's right, sets an upper limit.
It might limit how many you could build in the whole world, yes.
Yeah, if it's 100, it's hardly interesting.
I think it's more than that. I think there's
Yeah.
serious talk of making fuel cell hydrogen-based cars like mainstream. It's been seriously discussed.
The one thing they forget with that is the fact that it burns so hot that you still generate all the nitrogen oxides anyway.
I don't know.
Unless you have
It's
oxygen.
conceptually it's attractive, but the actual practical problems of building these things.
Exactly.
So I gave my Mars talk in Bath, like when I was just appointed as a consultant, and I had dinner before the thing with a guy. He was called Rod Scott, I think. I can't remember his surname. He was a professor of biology, and he organised a science cafe there. And he said that many of the things they're talking about in science fiction, not quite science fiction, it's near future technologies, some of which I wrote about for The Independent, I wrote about 55 articles for them a few years ago. Although they work in the lab, to make them work on industrial scale is an immense challenge. And if you could double their efficiency, he said to me, they would still be comical. So the things you can make work in the lab, maybe some politicians or optimists are saying, well, that would solve a lot of problems. But to make them work on a commercial scale is very difficult. But it doesn't mean it's impossible. Think about that guy lampooning SpaceX in 2013. You couldn't hear his voice. He was saying it was a dream, it's impossible with a bunch of nutcases. Neil Armstrong and his friend Cernan said, NASA should focus on Boeing and Lockheed Martin, SpaceX are a waste of time. They're never going to make this work. They're a bunch of nutcases. They've actually made a lot of stuff work. They've captured 80% of the global market. Think about this machine here in front of me now. This TV camera is better than the TV I used to watch as a kid on TV, the picture quality, and I can afford it as a normal person, normalish. I can afford it, yeah? So technology will advance. Think about the number of transistors and NAND gates on a silicon chip that goes up every few days. It's maximum capacity. Okay, so you then say something is technologically impossible to do, you're probably wrong. It's only a question of when we do it and how.
Right, so one last question. Right, that's the first hand I saw. Right.
It's all right, I'll just shout. Any thoughts on solar sails? Once we get up there,
Yeah.
use of solar sails, which
Solar
very
sails.
slowly
Yes, got it. Yeah. So solar sails. So that's more propulsion once you're in orbit. You want to go like under a planet. So one of the systems, this doesn't work unless we've got like a blackboard. We've got a pen for drawing on pictures on here. Right. So what you do, we haven't got one. Forget about that idea. Right. So what you do is you get some immense sail, literally very similar to a sail you have on a traditional sailing ship, and you unfold it in space. And it's made of something like tin foil, okay? And it could be realistically 1,000 meters wide and square. You attach something a bit like fishing line to it at various points as the guy ropes, and at the other end you have a payload, and the light from the sun hits the sail, and the photons of the light bounce off the sail, and the momentum transfer from the photons pushes you outwards away from the sun. Okay, it's a solar sailing. So you can, again, in the 1970s, I remember reading a book in 1979 as a kid, and they'd worked out for different designs of sail how fast they would go. And it's fabulous. You know, the whole problem with space travel is solved by solar sails. That's the way forward. And because it's a sailing ship, there's no fuel. Like if you had a yacht, you have to refuel it. You can sail across the Atlantic and sail back again using the same sail, so the wind keeps blowing. In fact, the wind blows day and night in outer space. It never stops. So it works. The problem is the practical problem of assembling something, and the sail works better and better and better the thinner the sail. Okay, so tin foil that you use in like your kitchen is much, much too thick. You're looking for something that's like cling film, that's, even if you play with cling film, it's gone out of fashion now. You wrap your sandwiches in them, it gets tangled quite quickly and you look like an idiot, yeah? But so you go to something like cling film, or maybe 1% as thick, that's silvered, and that you could build a sail as wide as possible. So a sail that was 2 kilometers wide would go faster than a sail that's 1 kilometer wide. So the technology to actually build it is very difficult. There's been some prototypes flown. The Japanese flew something to Venus, and they claimed it was working a bit. In fact, it would work better going to Venus inwards than it would going out to Mars, because the intensive sunlight goes up as you get close to the sun. So solar sails have been looked at, but they've not yet built a significant solar sail project that flies in space. But there are people talking about, there's chatter about it all the time in the space literature, and there's like computer diagrams of what it would look like. But with all these things, to actually fly something for real is hard. It costs money, the prototype might not necessarily work, and at least some of the problems associated with it when you try to build it would be quite difficult. But if it could work, it is fabulous. You could, with theoretical designs of sails, if you can make the materials super, super, super thin, they could go at incredibly high speeds, like just a few weeks to Mars, and then come back, change the astronauts, get some fresh ones, and go back again without any fuel, blown by the light from the sun.
Can be used for graphene?
Maybe, yeah.
Graphene, and it's relying on continuing developments in materials technology.
Yeah, so the design I saw years ago that I could half understand at the time was you make like a window frame, or maybe, you know those plastic rings you put in soap and you blow bubbles with them, yeah? And in this window frame, you create a sheet of wax in outer space, in zero gravity and in vacuum. And then with an aerosol can, you spray aluminium on it. There's a super thin veneer of aluminium. Okay, then you let it set, and then you put the whole sheet in a heating thing and you boil off the wax. The wax boils off in a container, and you recycle it, and you're left with a membrane of aluminium, which is like 20 atoms thick. And then you put these together like a mosaic, and then you have an incredibly lightweight sail. So the whole weight of the sail is spread over, so it's smeared out over such a large area. It captures the sunlight to blow you to another planet. But right now, I'm being hit by photons from this thing. Oh my god, it's on my face. Knocked over, right? But you don't normally get knocked over by the sunlight. You can't even feel it. You need very sophisticated equipment to even detect it. But there is momentum transfer. So to create a force big enough to propel a vehicle, possibly people in it, for several months at high speed, you need an enormous sail. But if you go Google on solar sails, it's all there. Endless research papers and optimistic discussions how we can use solar sails to go all over the place. So solar sails would be the solution if you could build one. It's like nuclear fusion is the solution to the energy crisis for sure, if you can build it. They haven't built it yet. They're getting close, but I don't know when it's going to happen.
Okay, good answer. I'd like to call upon Adam to propose a vote of thanks.
Thanks, Chris. Can you all hear me okay?
Yes.
Good. Okay, so, I mean, it's lovely